All right, so namaste and a warm welcome to everyone. So let's try to do a quick recap of what the objective of this course is, at least the first half of this course is, right? So the objective of this course is to study what we mean by simplicial homology, right? So what does simplicial homology mean? Well, loosely, simplicial homology means that if we are given some simplicial complex, then we would like to count the number of holes of different dimensions in the given simplicial complex, right? Like for example, if let's say this is the simplicial complex that has been given to us, then we would like to say that there are no two-dimensional holes or no one holes in this simplicial complex because there are no two-dimensional hollow enclosed regions. On the other hand, if you look at this simplicial complex, here indeed there is a hole and that hole is over here, right? So we would like to be able to conclude using some tools that indeed there is one hole here, whereas in this simplicial complex, okay, the difference between this simplicial complex and this simplicial complex is that there is an additional triangle in here, okay, if you can see, right? So because of this triangle, although there is an enclosed region, this enclosed region is filled. Okay, so because of this reason, we would like to say that, well, there are no holes in this simplicial complex as well, right? So we would like to say that there are no holes here, there are no holes here, but one hole in here. Okay, so that is what we would like to be able to do, right? So so in some sense, what we have been doing so far, okay, has been to build the tools that will help us draw such conclusions. Is that okay? So that is what we have been trying to do so far. So specifically what we did last time was the following. Let's say delta is some given simplicial complex, right? And for such a given simplicial complex, we did the following. For every integer p, right? So whether p is a positive integer, negative integer, or 0, for every such integer p, we define the vector space Cp given in the following way, right? So this includes formal sums of the following form, where AIs are elements of the field Z2 and sigma i's are the p-dimensional faces in delta. So I hope you agree that these vector spaces are defined based on the simplicial complex. So as the simplicial complex changes, this definition will also change, right? So by itself, this is a set. Okay, so in order to make it into a vector space, we defined the addition operation and the scalar multiplication operation in the following ways, right? So the addition operation was defined in the following way. Like, let's say this is one p chain. Okay, so as I mentioned last time, we will refer to the elements of Cp as p chains. Okay, elements of Cp would be referred to as p chains. Okay, so let's say we have been given some p chain which we denote as summation I ai sigma I. Okay, so observe that here I sort of start being a bit lazy in the sense that here I said I equals 1 to fp, but since this is going to be consistently used all the time, I don't want to repeatedly say it. I'll just say summation over I, and this has to be interpreted in the following way, that I goes from 1 to little fp, where little fp is the cardinality of the set of all p-dimensional faces, which means that fp denotes, this little fp denotes the number of p-dimensional faces in delta. So I won't repeatedly write these indices. It has to be understood from now on. I'll simply write summation I, right? So this is a p chain. This is another p chain. I claim this is another p chain because notice that I'm using some different coefficients over here, right? So when I want to add these two p chains, the rule is that I take these two coefficients, the corresponding coefficients, and add them, and think of that as the coefficient to be written in front of sigma I, right? So you can ask how do you do this addition? Well, notice that ai is an element of Z2. Similarly, ai prime is an element of Z2. So this addition you can simply do, right, based on the knowledge that you have about additions in Z2. Right, so that addition you perform over here, and in this way the addition between two p chains is defined. And similarly, here is the rule which specifies how to perform the scalar multiplication operation. Okay, so here x is an element of Z2. You perform a scalar multiplication between an element of your field and the element of your vector space, and the output is defined in the following way. So you can see that we write it in this form. So the coefficient of sigma I now is x dot ai, right? So this is a multiplication between two elements in Z2. Okay, so again, how you know how to perform multiplication in Z2. So this multiplication is defined in that spirit, right? So in this way, we define the addition and scalar multiplication operations, right? And we claim that for this addition and scalar multiplication operation, indeed the CP is a Z2 vector space. That is what we showed last time. And in addition, we also defined some, we also looked at these, different cases where P is less than -2, less than equal to -2, and P is bigger than dimension of delta, right? So in these cases, we said whether we are working with the usual homology or the reduced homology, CP will be the trivial vector space. So it just simply consists of some element which we will refer to as 0 and interpret it as the additive identity element. Okay, so this vector space only has one element, and that element we will denote it as 0, and it has to be interpreted as the additive identity element. Okay, and then we said, we will sort of define C minus 1 differently. Okay, so when I say we are working with usual homology, we will define C minus 1 as in this case, it will only be the trivial vector space. That is, it will only consist of one element, which is the additive identity, right? But when I say we are working with reduced homology, in that case, we will set C minus 1 to be Z2. Right, so some of you may have questions like why we are defining this way and so on and so forth. Okay, so it's a bit difficult to explain why we are defining it in this fashion. Okay, it will become clear later on. And also I would like to make one point here, right? See, this choice of C minus 1 equals Z2 is not something, that when it was first discovered, okay, people sort of said, oh, C minus 1 has to be Z2. Right, so it's not something like that. Instead, people came up with some definitions. Okay, they played around with it. They realized that, oh, this is complicated, there are some issues with it. How do I deal with these issues? Okay, maybe perhaps if I set C minus 1 in this fashion, maybe it will resolve some of these issues, and so on and so forth. Right, so you can see that in that sense, okay, there is a lot of back and forth that happens. That is, you start out with some candidate definition. You work with that definition, you realize that that is not good enough. Then you come back, rework the definition, come up with a new version of the definition. Then you start using that definition. Later on, you see that, oh, this definition still has issues. You go back, refine the definition one more time, and so on and so forth. Okay, so once you start doing research, you will realize that there is a lot of this refinements that keep going on. Okay, however, once something is written as part of a textbook, or something is written as part of a paper, okay, they write it in a form so that it is easier for the audience to read and understand what they are trying to say. Okay, so in that sense, they don't talk about all the different trial and errors that they had adopted to eventually affix this final form of the definition. Right, so in that sense, whenever as a student, or whenever as a audience, when you read a paper, you are not able to really appreciate at first glance why did someone define it in this fashion. Okay, so currently it is indeed the case that why we are working with C minus 1 equals Z2. In fact, it's not even clear why C minus 1 equals 0 makes sense. Okay, so at this point, it's fine if you don't understand, because I have not really given you the motivation. The motivation will become clear, okay, over the next lecture or two. Okay, why we are defining it in this fashion and so on. Okay, but nevertheless, the bottom line is that in the previous class, we managed to define for every integer p some vector space, right? So either it is defined using the faces of this simplicial complex delta, or it would be defined to be the, or it is said to be the trivial vector space, or in some cases it is said to be Z2 itself. Okay, so again, I would like to emphasize that Z2 is a field, but a field can also be viewed as a vector space over itself. Okay, so this is something that you should verify on your own. So for example, R indeed is a field. This is the set of real numbers, but it can also be viewed as a vector space, right? So it can be viewed as a vector space over itself, where the vectors come from R, the scalars also come from R, right? So you can sort of verify that, for every field, let F be any field, then that field can itself be viewed as a vector space over itself. All right. Okay, so in that sense, this also is a vector space, right? So we now have a vector space for every integer p, right? And today we are going to sort of decide what to do with these vector spaces, right? So we have defined these vector spaces, but let's recall that our goal is to identify these holes in these simplicial complexes, right? And slowly it will become clear what's the purpose of defining these, weird looking vector space and so on and so forth. All right. Okay, so now we have these vector spaces. So let me write these vector spaces, right? So you have, let's say, c minus 2, c minus 1. So let me put dot dots. You have the c0, you have c1, you have c2, you have c3 dot dot dot. So you can see that for every p you have some vector space, right? So now what I'm going to define is, I'm going to define a vector space homomorphism between these vector spaces, right? And notice the sign of the arrow. Okay, it goes from in general from CP to CP minus 1. So you can see that I have drawn this arrow to indicate that I'm going to define a map which goes from C2 to C1. Similarly, I'm going to define a map which goes from C1 to C0 and so on, right? And I will denote these maps in the following way, right? So this will be denoted as daba 3, this will be denoted as daba 2, this will be denoted as daba 1, this will be denoted as daba 0, and this will be denoted as daba minus 1, and so on, right? So what I'm going to do is, the goal over the next couple of minutes is to define some homomorphism that goes between these vector spaces, right? So let's be a bit more specific. Okay, so we will first define this this homomorphism, okay, between for p which takes values between 1 and dimension of delta. Okay, so we will later on extend this definition to cover other p cases as well, but to begin with, we will consider the case where this p lies between 1 and dimension of delta, and this daba p, okay, this will be a map which goes from CP to CP minus 1, right? And we will refer to this map as the boundary operator. It will become clear why we are going to refer to it as the boundary operator, right? And the definition of this boundary operator is as follows, right? So recall what CP is, right? So CP is summation AI sigma I such that AI, these coefficients lie in Z2 and these sigma i's lie in FP of delta. Okay, so this is what we recall, right? So now, we can think of sigma I being one of the P chains, right? So although I am writing sigma I, the way you have to interpret this sigma is that you have to interpret this as 0 sigma 1 plus 0 sigma 2 blah 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 plus 1 sigma I plus 0 sigma I plus 1 blah 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 all the way up till 0 sigma FP, right? So when I say sigma I is one of the P chains, you have to interpret this sigma I in this fashion, right? So you can see that there is a 1 in front of sigma I, but for all other sigmas, the coefficient in front of it is 0. Right, so this is indeed one of the P chains, right? Or this is one of the elements in CP, right? So now what I'm going to do is, in order to define this daba P, I'm first going to define this daba P for this special P chain sigma I, right? So let's try to define it. Okay, so let sigma be one of the P faces. Okay, so let sigma be one of the P faces in delta, right? So sigma will be made up of P plus 1 vertices. So let's denote these P plus 1 vertices in the following way: V0, V1 all the way up till Vp. Okay, so let me repeat this. Let sigma be a face in your given simplicial complex delta. So this is a P face or a P dimensional face. Since it's a P dimensional face, it will have P plus 1 vertices. Let us denote these P plus 1 vertices as follows: V0, V1, V2 all the way up till Vp, right? So as I said, this sigma, okay, this is indeed a subset of the vertex set, but you can also imagine this sigma as a P chain, right? So the way to imagine it is as I mentioned over here, right? So sigma is some arbitrary sigma I, and as I said, you can interpret sigma I as a p chain in the following way. Similarly, if I give you some arbitrary sigma, you can interpret it as a p chain, right? So why am I insisting that you have to interpret it as a p chain? Because this operator takes the domain of this operator is the set of p chains. Is this okay? So that is very, very important. The domain of this operator is the set of p chains. That's why it is important that I interpret sigma as a p chain so that I can operate this operator on this sigma, right? So how is this daba p operator defined? So whenever you give sigma as an input to daba p, the output is as follows, right? So let's try and go over the output piece by piece. Okay, so it has a summation. The indices of the summation go from j equals 0 to p. Okay, so the indices of the summation go from j equals 0 to p. Okay, so this corresponds to these different vertices that we have, right? And the sum consists of sets, right? So you can see that there is a set here which is given as input, and the output is a sum of sets. So we will sort of formally interpret what these things mean, right? So what are these sets made up of? Okay, so notice that you have V0 all the way up till Vp. However, on top of this Vj, you see there is a hat symbol present. Okay, so let's try and interpret what this hat symbol means. The hat symbol implies that the corresponding vertex is to be dropped. Is this okay? So the hat symbol implies that the corresponding vertex has to be dropped. Okay, so this is how this operator is defined, right? So let's try to look at an example. So let's say this is the simplicial complex, right? And this daba one will go from C1 to C0. Is this okay? So this is the set of all 1 chains in this simplicial complex, and this is the set of all 0 chains in this simplicial complex. So I hope you agree that V1, V2, right? V1, V2 is one of the edges of delta, and you can interpret this set V1, V2 as a 1 chain, right? So you can interpret this as in the following way. So this is sorry, I shouldn't put a dot here. So this is 1 V1 V2, okay, plus 0 V2 V3 plus 0 V1 V3. Okay, so you can see that one can interpret this as a 1 chain. Is this okay? So this 1 chain I am giving as input to daba 1, and the output to that is this 0 chain. Okay, so I am claiming that the output of this 1 chain is this 0 chain. So how have I obtained this 0 chain? Well, what I do is I drop. So notice that in this input there are 2 vertices, right? So I drop one vertex at a time, and whatever I am left with I write over here. So let's say I drop the first vertex. Okay, so maybe I'll follow the definition over here. So instead of writing it as V1 plus V2, let me write it as V2 and V1. Okay, so it will become clear why am I doing this. Of course, it doesn't matter because of the commutativity property. All right, so what I'm going to do is I'm going to first drop this vertex. So as soon as I drop this vertex, the set will only include V2. Next, I'm going to drop this vertex, and I'll now be left with only V1, right? So this is V2 plus V1, and you can interpret this as 1 V1 plus sorry, I shouldn't put a dot here. So this is 1 V1 plus 1 V2 plus 0 V3. Okay, so in this sense, you can see that we took a 1 chain, applied this operator, and this gave us a 0 chain. Is this okay? So this is how this operator works. Now, I would also like to emphasize why we refer to this as the boundary operator. Okay, so why do we refer to this as the boundary operator? Well, the reason is that it takes a face, let's say something like sigma, and spits out its boundary faces or a combination of its boundary faces. Okay, so what do I mean by that? Let's look at this face over here. So you have this V1 V2 face, right? Its boundary is made up of these vertices V1 and V2, right? So if you give this edge as input to this boundary operator, it will spit out V1 plus V2, which you can see is the boundary elements of this edge, right? So similarly, let
Sir, you have been muted.
You have been muted, sir.
can you hear me now?
Yes, sir.
Yes.
When was I muted? Were you able to hear me, or was I muted from the beginning?
No, since the start of this page.
Okay, so I don't know who muted me. I did not mute myself, but please don't mute me if you are interested in hearing the lecture. Okay, thank you. Okay, so what I wanted to say was that why we refer to these daba p's as boundary operators. So I wanted to give you one more example. So let's look at this simplicial complex. I hope you agree that v1 v2 v3 is a two face of this simplicial complex. Now since this is a two face, you can interpret it as a two chain, which means it's an element of c2, and now I can apply daba 2, right? So by following the rule, I have to draw one vertex at a time. So I'll first drop the first vertex, then I will drop the second vertex, and then let's say I drop the third vertex, right? So then I drop the third vertex. Sorry, it should be v1 v2. So it should be v1 v2, right? So again, you can see that if you give a triangle as input over here, right, the boundary faces are these three edges, and you can see that once you apply this operator, you get a combination of the boundary faces, right? So in this sense, you can see that if you give a p face as input to daba p, right, the output will be this the combination of its different p minus 1 boundary faces, right? So if you give a two face, the output is the combination of the different one faces, which are the boundary of this two face. So in general, if you give a p face, right, so let's say sigma is a p phase, right? So let's say this is a p phase, then daba p of sigma, okay, will be a combination of p minus 1 faces in the boundary of sigma. Okay, so it is because of this reason that daba p is referred to as the boundary operator. So let me pause here for a second or two. If there are any questions with regards to the definition of daba p and why it is referred to as a boundary operator, this may be a good place to ask. Please go ahead. Yes, Jacob, go ahead.
In the operator daba p, suppose we are applying it on v1 v2 plus v2 v3.
Yeah, so that I will now define. I haven't yet defined.
Okay.
So that is still remaining. Okay. All right. Okay, so now let's advance. So as you saw, okay, to begin with, we wanted to define this daba p from cp to cp minus 1, and as most of you must have realized, okay, this is not a complete definition. This is not a complete definition because I have defined this daba p operator only over special p chains, right? So special p chains meaning those p chains where these ai is 1 for precisely one I, and for every other I the AIs are 0, right? So you can think of one P face as this special kind of a P chain, right? So only for those P chains have we defined this this operator. But I hope you remember that this for this vector space CP, the set sigma 1 to let's say sigma FP, this forms a basis, right? This forms a basis, right? This is what we saw and proved last time, and from that we concluded that the dimension of this vector space must be little fp, right? That is what we concluded. All right, so at this point, what is more important is that sigma 1 to sigma fp, okay, forms a basis of cp, right? So although I have defined this daba p only for the special p chain, right? However, above I had mentioned that we want this to be a vector space homomorphism, right? So from this phrase itself, you should be able to see how one should be able to define DABA P for a generic P chain, right? So let's just see what we have to do, right? So if we, so you can think of this input, okay, as A1 dot sigma 1 plus A2 dot sigma 2 plus blah 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 all the way up till AFP dot sigma FP, right? So notice that the scalar multiplication operation is only defined between a field element and a P chain, right? Whereas here sigma 1, I have written it as sigma 1, but you should not interpret this sigma 1 as a face, but you should rather interpret this as a P chain, and this has to be interpreted like 1 sigma 1 plus 0 sigma 2 plus blah 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 plus 0 sigma FP, right? So I'm stressing this so that you also be careful that it's clear to you that, oh, this scalar multiplication operation is being defined. Is it true that the element on the left is a field element, the element on the right is a vector space element? So all these things you need to ensure as well. Okay, so that's why I'm trying to stress that although I have written it as sigma 1, this is indeed a P chain because you can interpret it in this fashion, right? And you can think of this generic element, this generic P chain, as a linear combination of these different basic P chains. Is this okay? So you can interpret this as the linear combination of this. And since we want this DABA P to be a vector space homomorphism, which is equivalent to saying that we want this to be a linear map. So since we have given as input a linear combination of these special inputs, the outputs should be the same linear combination of the corresponding outputs, right? So DABA P of summation I AI sigma I, okay, you can interpret it in this fashion. So this is a linear combination of sigma 1, sigma 2 and sigma FP. So this is a linear combination. So the output should be the corresponding linear combination of the corresponding outputs, right? So what is the output of sigma I? Well, it is DABA P sigma I, right? So you take that and perform a scalar multiplication between AI and this, and then you sum it up, right? So this is how you would want this map, this is how you would ensure that this map is a linear map, right? So this is something that is basic that one would require. Okay, so let me pause here for a second or two. I hope from this definition it is clear that how DABA P needs to be defined for different for any given P chain. Okay, so this definition covers all possible cases. So at this point you should be clear how this is defined, right? Maybe we will look at an example and that will make things a bit clear for you. Okay, so let's look at this simplicial complex over here, right? So this simplicial complex has 3 vertices, V1, V2 and V3, and it has 3 edges, V1, V2, V2, V3 and V1, V3. Is this okay? So we saw if we gave this special P chain or one chain as input to DABA 1, we got this as the output. Right, now let's see what will happen if we gave this generic P chain, or this of course it's not generic, but this is maybe more complicated one chain as input to DABA 1, right? So so this one chain is made up of V1, V2, V1, V3. So this is the first edge, the second edge and the third edge, right? So let's see what will happen if we gave as input these this one chain, right? So I hope you agree that this is a one chain and I'm giving this as input to DABA 1, right? So so the output will be, you first take the output of this. So the output of this would be V1 plus V2. Then you take the output of V1 plus V1 V3. This is V1 plus V3. Then you take V2 V3 and you look at their outputs, that is V2 plus V3, and you take the sum of all these outputs, right? So the final output will be V1 plus V2 plus V1 plus V3 plus V2 plus V3. And you will notice that V1 appears twice since we are working with Z2 coefficients, right? This V1 plus V1, okay, is, recall, you can interpret it as 1 V1 plus 0 V2 plus 0 V3. And this also you can interpret it in this way. So if you add V1 to V1 based on the addition rule that we have just discussed, I hope you agree that the output for this would be 0, right? Similarly, V2 plus V2 would be 0 and V3 plus V3 will be 0, and 0 plus 0 plus 0 is also 0, and we end up with 0, right? Okay, so there are two ways to look at it. First is, from the definition of DABA 1 perspective, okay, I can now indeed compute the output of DABA1 over these different one chains, right? That is one way to look at it. But it should also interest you that, this DABA1 took this chain, this one chain to 0. Whereas in this case, that is the case that we saw above, where, we looked at this special one chain. Okay, the output was not 0. V1 plus V2 is not 0. Whereas, this sum is indeed 0. Now let's try to understand, okay, why is this interesting to us, right? So notice that this p chain that we looked at now, or this one chain that we looked at now, I hope you agree it is the combination of these three edges, right? It's the combination of these three edges. Now this is special for us because, as you can see, these three edges together enclose a two-dimensional hole. Okay, and the two-dimensional hole, I hope you agree, you can see over here, right? So you can see that there is a two-dimensional hole here, right? And these three edges sort of enclose this two-dimensional hole, right? And it is interesting to note that this DABA1 operator takes such a one chain and maps it to 0, right? So this is sort of you can think of as being one of the key reasons for defining DABA1 in this fashion, in that it takes patterns of our interest. Okay, so here patterns, you have to interpret it as interesting p chains, and here interesting means that these p chains enclose a p plus one dimensional hole, right? So you can see that such this operator actually takes such patterns or such interesting p chains, okay, to 0. Is this okay? So that's the reason, okay, why we are defining this DABA P operator in this sense. Okay, and you will sort of slowly start to appreciate why this DABA P operator is defined, the way it is defined over here. Is this okay? So let me pause here for a couple of seconds. If there are any questions, this may be a good place to ask. Let me know. So if you have any questions with regards to how is DABA P operator defined, okay, why it is defined this way, and so on and so forth, this may be a very good time to ask. Please let me know. Yes, Agnit, go ahead.
So this is defined for all p greater than or equal to 1 or 0.
So it is defined for the time being between all p between 1 and dimension of delta. So which means that DABA p, so like the boundary case would be p equals 1, which means that DABA p is defined for like DABA 1, okay, which goes from C1 to 0. So this definition we have covered, and similarly DABA, so let's say this is D. So we have covered DABA D as well, which goes from CD to CD minus 1. Does that answer your question?
Yes.
Okay, so we have not covered other cases in this definition, because in those other cases, either one or both the vector spaces are defined differently in comparison to the way CP is defined over here. Okay, so that's the reason I want to, so here is the way, CP is defined for P between 1 and dimension of delta, right? For all other cases, either one of the vector spaces or both the vector spaces are defined in a different spirit. That's why I want to cover those cases separately. Okay, so you are right that at this point we have only defined this DABA P when P lies between 1 and dimension of delta. Okay, we will soon extend this definition to cover the cases when P lies outside this range. Okay, so so I hope this is clear. Okay, so now we will do a quick test. Okay, so I will sort of speedily go over this discussion, but nevertheless, if you didn't understand, I request that you go home, carefully go over the steps that I have written over here to make sure you understand it for your own sake. Okay, so what we are going to do is that we will verify that this DABA P operator that we have defined in this way, okay, using this definition that we have over here for the special P chains. Okay, this DABA P operator indeed is linear. right? This is what we are going to verify. So linear means that it's a vector space homomorphism, right? So some of you may ask, oh, didn't we verify that it's a vector space homomorphism? No, right? Here we just said that if we want this DABA P to be a vector space homomorphism, then it is natural to expect that for any generic P chain, the definition should be given in this fashion. However, from here we have not verified whether DABA P is linear or not. That's what we are going to do now, right? So in order to verify whether DABA P is linear or not, here is the standard test that you must have studied in your course on linear algebra. Okay, so let me take two P chains. So the first P chain is summation over I AI sigma I, and this other P chain is C prime, where the coefficients, as you can see, are different. So in this case, they are AI primes. So this is some P chain, this is some P chain, and let us take two different coefficients from Z2, right? And let's take this linear combination over here. So you take this P chain, take a scalar product with X, take this P chain, take a scalar product with X, and then you add them up. So you can see that this is a linear combination, right? And our goal is to check, okay, so maybe I'll say aim to check if DABA P of X dot C plus X prime dot C prime, okay, this indeed equals X dot DABA P of C plus X prime dot DABA P of C prime. Okay, so this is what we are going to check. And I'll quickly go over the discussion, but you should be able to derive each of these steps on your own. So I request you to go home and read it carefully. In case you don't understand any of it, you can ask me later on as well. All right. Okay, so first let's see if we can get a simplified expression for this linear combination over here, right? So recall that C is summation AI sigma I. So if I do this inner product, sorry, not inner product, this scalar product X dot C, I hope you agree that we will end up with something like this. Okay, so here in order to be precise, I should have written it as X dot AI. Formally say that we are taking the dot product between, or the multiplication between, two field elements. However, I'll write it as xai, okay, so that I can reduce some of the notations. Okay, so I'll just write it as xai. So this is the coefficient in front of sigma I. So this is the scalar multiplication rule that we have studied, right? Similarly, we have this C prime, which is summation AI prime sigma I, and I'm now going to do a scalar multiplication between X prime and C prime. So we will end up with summation over I X prime AI prime sigma I. Now I have to do this addition operation, right? So the addition operation is that you take the corresponding coefficients, add them up, right? So you will end up with xai plus X prime AI prime, right? And you add these things up, and then you will end up with this final P chain. Okay, so you started off with a linear combination of two P chains, and this is the final representation. So this is the final generic representation for the linear combination that we took above, right? For such a P chain, okay, we know how DABA P operates, right? Because this can be viewed as a linear combination of these basis P chains, right? So these sigma i's can be interpreted as these basis P chains, and for such a generic P chain, we know how the DABA P operator works. So from this we can conclude that DABA P of X dot C plus X prime dot C prime must be DABA P, which is operated on this, right? And we know how the output should look like. So it should be sum over I, whatever is the coefficient here, you write this coefficient over here, take the scalar product with DABA P of sigma I, right? So this is from the way we have defined this DABA P operator, right? And now what we will do is we will do some basic algebra in order to verify whether this expression over here is indeed X dot DABA P of C plus X prime dot DABA P of C prime. Okay, so this is what we are going to quickly verify, right? So what we are going to do here is that notice that here you have the addition of these scalar elements, and then you have this dot product with a vector, right? So we know that this CP minus 1 is a vector space, so which means that this addition and this scalar multiplication operation satisfy the distributivity property. Hence you can sort of distribute this plus over this scalar multiplication, and you can write this as xai scalar product delta p sigma I plus x prime ai prime dot scalar product with daba p sigma I. So this is the distributive property that we are making use of over here, right? And then what we are doing is that, notice that you have summation I over this entire expression, right? So now what I'm doing is I can break this summation and I can write it in this fashion, right? So notice that here I have a summation I here I have a summation I over here. So it is not just manipulating your expression just because we can do it, but there are specific reasons, right? So what does this expression mean? This expression means that for every I, you first do this addition, okay, and then add the corresponding outputs for each I. Whereas what we have written over here corresponds to saying that you first take the additions of these elements for different values of I. Whatever is the output, you note it down. You go over here, you take all these entries for different values of I, add them up. Whatever is the output, you note it down, and you add the final outputs together. So you see that the order in which you perform the addition is different in this expression and this expression. However, we know that the addition is commutative, so it doesn't matter in which order you perform. In fact, I should say that it's also associative, right? So associative means that if you have more than two elements, which two elements you add first doesn't matter, right? So from this property, it's easy to see that you can break this sum in this fashion, right? So this follows from the commutativity and associativity property, right? And then let's focus on these individual sums, right? So these individual sums, you can write it in this fashion. So let me just elaborate what this is, right? So this is your x dot ai dot daba p of sigma I. So how is this different to this? Well, here what you do is you first multiply x and ai. Whatever is the output, you multiply it with this daba p of sigma I. Whereas on the other hand, what you do over here is you first take ai, do the dot product with daba p of sigma I. This will be one p minus 1 chain. Whatever is the output, you take that and perform its dot product with x. Similarly over here, right? So you can write this in this fashion because of some property called as the compatibility property, right? So you can verify this compatibility property and show that indeed this expression one can write in this fashion, right? Now what I'm saying is that so you can see that there is some addition going on over here, and then there is some dot product going on over here. So we know that this dot and this plus operation, they satisfy the distributivity property. So you can take this x outside, okay, and write it as x dot of this sum, right? So we know that x dot of this sum is equal to sum of x dot of the individual elements. Okay, so this just follows from the distributive property. Similarly, you can write this expression as x prime dot summation I ai prime. So I should have a dot over here as well, dot daba p of sigma I, right? But this expression that we have over here, okay, this indeed is daba p of c, and similarly this indeed is daba p of c prime, right? You can recall that c is summation ai sigma I, right? Summation ai sigma I, and consequently daba p of c must be summation I ai dot daba p of sigma I. So you can see that we indeed have this expression over here. So this is daba p of c. Similarly, we have this expression over here. So this is daba p of c prime, and you can indeed see that this is the way we desire it, right? So from this one can verify that daba p is linear, or alternatively daba p is a vector space homomorphism, right? So I verified this in some speedily fashion. I request you to verify it, but it is important that you understand why each of these properties make sense. Okay, so we just don't define it for the fun of it, or for the just because somebody else is defining it. Each and every definition has some purpose, and we are sort of fully utilizing that purpose over here. Is this okay? So I request you to go over it and make sure that you are able to appreciate what is happening in each of these steps. Okay, so I agree that I went over it quite fast. So it's fine if you didn't understand it, but I want you to appreciate that we verified every step, right? We just didn't say something happens because it happens somewhere else. We didn't sort of use such justifications. We didn't say somebody has said somewhere, that's why we have it. We didn't use such loose arguments. We were precise in saying that, look, this is a vector space, so we can make use of the distributivity property, we can make use of this compatibility property. So all the specific properties we have used, and finally managed to verify that indeed DABA P is a vector space homomorphism. Okay, so let me pause for a second or two. If you have any questions, please ask. All right, so I don't see any raised hand, so maybe we can advance. Okay, so what we have done is, we have managed to verify that, for 1 less than p less than dimension of delta, we define this, boundary operator, okay, which goes from Cp to Cp minus 1. We defined it, and then we verified that the way we define it ensures that our DABA P operator is indeed a vector space homomorphism, or it is a linear operator. Okay, so this is what we managed to verify. All right. Okay, so now as one of you pointed out explicitly, and I'm sure most of you must have noticed that we haven't defined this DABA P operator for p less than equal to 0 and p greater than equal to dimension of delta plus 1, right? So for all other p's we define. So for such p values we have already defined how the DABA P operator behaves. So now we will focus on these different choices of p, right? So now let us focus first on the case where p is less than equal to -2, right? So we are sort of not focusing on the case where p is 0 or p is -1 for the time being. The reason is that in the usual or the reduced homology, the definition of c minus 1 is different. So let's tackle that separately. But instead, let's focus on the case where p is less than or equal to -2, or p is bigger than dimension of delta plus 2, right? So here we are sort of ignoring the case, or I shouldn't say ignore, we are sort of not looking at the case where p equals dimension of delta plus 1, because this also we will deal with separately. Okay, so let's look at this case and this case, right? So we can deal with all these p ranges together, because for whatever p you choose over here, Cp and Cp minus 1, both these vector spaces will be the trivial vector space. Is this okay? So in one shot, we will be able to define DABA P for any P which satisfies these conditions, right? So in both these cases, as I mentioned, the Cp and Cp minus 1, both are these trivial vector spaces, which means that it only includes one element, which we will denote it as 0 and interpret it as the additive identity, right? So I hope you agree that this is a Z2 vector space. This is a Z2 vector space. And the addition operation is defined in this fashion: 0 plus 0 is 0, and 0 dot 0 is 0, and 1 dot 0 is 0, right? So this is the scalar multiplication operation, and this is the addition operation that we are defining, right? So again, it should be clear that this 0 is from Z2, whereas this 0 is your 0 from Cp, right? Similarly, this one is from Z2 and this is from Cp, and these zeros again are from Cp. Similarly, these 3 zeros that we have written over here, right, those are also from Cp. Okay, so I hope this is clear. So now I have to define DABA P, right? So the domain consists of only one element, right? The domain consists of only one element, 0 over here, and the codomain also consists of one element, right? So in some sense, you are left with no choice, right? So the only way you can map this 0 is you have to map it to the 0 that is there on the other side, which means that this is the 0 which is in the domain, which is Cp here, and this is the 0 which is the additive identity in the codomain. So we are left with no choice, because the domain only has one element and the codomain also has only one element, right? So in that sense, we have no choice, and we have to map this 0 to this 0, right? But nevertheless, this justifies why we chose this CP minus 1 to be the trivial vector space, right? So let's try to appreciate the reason for defining CP and CP minus 1 in this fashion, right? So I'll do a slight digression and emphasize that for any linear map, right? So forget about these boundary operators and things like that. My claim is that you give me any linear map. So linear map, recall, goes from some vector space to another vector space. So let's say T is such a linear map which goes from one vector space V to another vector space V prime, and we claim that, let's say, T is linear. Then my claim is that whatever be this linear map, under T, the additive identity in V should get mapped to the additive identity in V prime. Okay, this is a necessity for T to be a linear map, right? So let's look at a quick proof for this. I'm sure most of you must have studied, but this is very short, so I can do it quickly. Okay, so we will use proof by contradiction, and we will suppose that this claim over here is not true, which means that the additive identity of V is not mapped to the additive identity of V prime. So let's say T of 0 is Y, where Y is not equal to 0, right? So again, I would like to stress that although I use 0 over here, okay, you should interpret it appropriately. This 0 is the additive identity of V, whereas this is the additive identity of V prime, right? So let's verify why this claim leads to a contradiction, right? So of course, see, T is a map from V to V prime, so the additive identity has to be mapped to some element in V prime. But it could be the case that this output is not the additive identity of V prime. So that's what we have writing over here, that T of 0 equals Y, where Y is not equal to 0. Right. However, since T is linear, I hope you agree that, because of 0 being an additive identity, I hope you agree that 0 can be written as 0 plus 0, right? So from this, one can see that Y equals T of 0. This is from the way we have defined Y, right? Now 0, I can write it as 0 plus 0. So T of 0 must equal T of 0 plus 0, because 0 plus 0 is precisely 0. Now, since T is a linear map, I can write it as T of 0 plus T of 0, right? And above we have defined T of 0 to be Y, and this T of 0 should also be Y. So what we have managed to show is that the Y, which lies in this V prime vector space, must satisfy this condition over here. That is, Y must equal Y plus Y. Now, since Y lies in a vector space, and under the addition operation, along with the addition operation, this vector space is an abelian group, right? So every Y must have a inverse element. So let minus Y be the additive inverse of Y, and you can add that to both sides of this equation, right? So if you add minus Y to both sides of this equation, so this side will get you the additive identity of V prime. On the right hand side, because of using this associativity property, you can first change the order in which you do the addition, and this part, by the fact that you are adding Y to its additive inverse, you get the additive identity, and this is as it is. Now 0 plus Y is Y, because 0 is the additive identity. So what you manage to show that the additive identity must indeed equal Y, right? So this leads to a contradiction, because we had presumed explicitly that Y must not equal 0. So from this, it follows that indeed it must be the case that Y must be 0. In other words, whenever you have a linear map which goes from V to V prime, T of 0 must equal 0. Okay, this must always be the case, right? So because of this reason, and because we want to work with vector spaces, it makes sense that we define these CPs, okay, to be the trivial vector space. Is this clear? So let me pause here for a second or two. If you have any quick questions with regards to what I just did, and in particular trying to appreciate why we defined this CP to be this trivial vector space. Okay, the reason is that in that way we can ensure that this Daba P operator, okay, is indeed a linear map, right? The Daba P which goes from the trivial vector space Cp to Cp minus 1. So let's look at the case where both these are trivial vector spaces. Okay, by defining Cp and Cp minus 1 in this fashion, one can ensure that this definition of Daba P is also a linear map or a vector space homomorphism. Is this okay? So if you have any questions, please ask. Yes, Durjati, please go ahead.
Is there any significance if P is less than -2? Like different homology groups might have different sets for P less than 2 CP.
I'm not sure if I understood your question. So you're asking why are we working with P minus 2? Is that your question?
Yeah, is there any significance for different topological spaces? Like their definition would be different.
So they will not be different. So what you are saying is that for P minus 2, if I change my abstract simplicial complex, would I keep changing the definition of Cp for P less than -2? Is that your question?
Yes.
So I'm saying that no. So your question is, are they going to be significant in being able to distinguish between the topology of different simplicial complexes? No. All we are saying is that, okay, this way, we are sort of covering all ends. Okay, so this is just to make sure our definition is complete and there are no gaps and so on and so forth. Okay, and this also allows for some flexibility. Tomorrow, if we want to add some additional, things to this definition, there is some, place where we can do some modifications. But at this point, there is really no way in which Cp for P less than equal to -2 can be used to distinguish, or if it plays a significant role in the study of topology. But at this point, this is just to make sure algebraically we can do things for all P, and there is nothing special about any P. For every P we can define it in this sense. Okay, so that's the only reason. All right. So let us advance. Okay, so what we have managed to show is that for any P less than equal to -2 and for any P bigger than dimension of delta plus 2, okay, we can define this Daba P. Okay, so now three P values are remaining. The first is P is 0, -1, and the last is dimension of delta plus 1. Okay, so for these three values, we still haven't defined this Daba P operator, which we will do now. Okay, and we will carefully go over it. Okay, so let's look at the first case. Let's say P is dimension of delta plus 1, right? So let's first understand why are we discussing this case separately. The reason we are discussing this case separately is that here Cp is 0, right? In other words, Cp is the trivial vector space. However, if you look at Cp minus 1, right? So Cp minus 1, which means that, so let's say, a dimension of delta is d, right? Then P over here is d plus 1 and P minus 1 is d, right? So this Cp minus 1 is not going to be the trivial vector space. It will be made up of these formal sums, because this collection of d-dimensional faces in delta is not going to be empty, right? So that is the reason this Cp minus 1 is different to Cp, in that while Cp is the trivial vector space, Cp minus 1 need not be the trivial vector space. So this is the reason why we are discussing this P case differently. So the reason is that here it's not the case that both Cp and Cp minus 1 are trivial. Instead, it is the case that Cp is trivial, whereas Cp minus 1 is not, right? So let's now see how we can define the Daba P operator, right? So what do we have? In the domain side, we just have 0, right? So this is Cp, whereas in Cp minus 1, we have 0. So I should not say this, but instead write it this. So we have 0, we have, let's say, sigma 1 and sigma fd, and we have these different combinations, that is sigma 1 plus sigma 2, sigma 1 plus sigma 3, and so on. And finally you have this big d chain, which is sigma 1 plus sigma 2 plus blah 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 plus sigma fd. Right, so in this way I'm covering all possible d chains that one can construct. Okay, so these are the different d chains, right? Now what I have is, we on the domain side I have only one element, and on the codomain side you can see we have several elements, right? So the question that one needs to ask is, how should I define a map, right? So I can, map it this way, or I can also map my zero element to this and so on, right? But as you just saw, if we want to define a vector space homomorphism, we require that the zero be mapped to zero itself. Otherwise it will not be a vector space homomorphism, or it will not be a linear map, right? So because of this reason, okay, the way we will define this map is that we will map 0 to 0 itself, right? And that is what I have specified over here, right? So again, one can see that by this definition, this Daba P operator is actually a linear map. So you can check it. So what do I mean by checking it? Well, you have to take linear combinations of elements in the domain. So the elements in the domain are, 0 only, right? But, you can take these different linear combinations, which is a1.0 where a2.0, where a1, a2 lie in z2, right? So you can take this linear combination, right? But a1.0 is 0, and this is also 0. So this will be 0 plus 0, and 0 plus 0 is 0. So Daba P of 0 will be 0 itself, right? And this one can write it as a1.0 plus a2.0, and this is a1 dot Daba P of 0 plus a2 dot Daba P of 0, right? So this is some, at first it may look very stupid, but while I agree with you, but it is also ensuring that the way we are defining things ensures that this Daba P is indeed a vector space in the literal sense, right? We are not just saying things and we are not able to verify. So those things will never happen. When we say something is a vector space, you will be able to verify that if you give a linear combination of inputs, as input to Daba P, the output of this can again be expressed as a linear combination of the corresponding outputs. Okay, so that's what I sort of verified over here. All right. So now moving on. Okay, so now what remains is to define this Daba P operator for these two cases, that is P equals 0 and P equals -1. Okay, so let's first look at the case where let's look at the usual homology case. So in the usual homology case, this C -1 is 0, right? So C -1 is 0. So let's first try to define Daba -1. So Daba -1 goes from C -1 to C -2. Both these vector spaces are trivial. So, we are left with no other choice but to map 0 to 0, and we are done. Right now, let's look at the case of Daba 0. So Daba 0, we need to be careful because this C0 over here is not trivial. Right, C -1 is trivial, but C0 need not be trivial. So let's just understand what we are having. So C0, recall, is these different zero chains. So let's understand what we have. We have 0. So let's say there are like, V1 to Vf0. Okay, so these are the different vertices in this given simplicial complex. Then I hope you agree that the different zero chains will be V1, V2 all the way up till Vf0. Then you will have V1 plus V2, you will have V1 plus V3, and finally you will have this big zero chain, which is V1 plus V2 dot 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 plus all the way up till Vf0. Right, so in this way you will have these different zero chains in your domain. On the other hand, in the codomain you just have 0. Right, so I hope you are able to see this is the situation. C0 is what I have drawn over here. C -1 in the usual homology is the trivial vector space. Right, so again one can ask, how do I map? Again, you can see that you don't have any choice. Okay, you have to map every element in the domain to one element in the codomain, right? So you have no choice but to map every element here to this 0 that you have over here, right? You have no other choice. Okay, so in this sense, what we are claiming is that you give me any zero chain in C0, the Daba 0 operator will map this C to 0, which is there in the codomain. So we have no other choice, right? And one can check that the way this Daba 0 and Daba -1 are defined, you can indeed check that they are vector space homomorphisms. So let me pause here for a second or two. If there are any questions with regards to how we define Daba 0 and Daba -1 in the usual homology case, please ask. Do you have any questions with regards to the way we define this, Daba 0 and Daba -1? Please let me know. Whatever be your questions, please feel free to ask. Don't hesitate. Please don't think that you are the only one who is not understanding and things like that. If you have a question, please ask. If it's easy, I'll answer it now. If it's going to be time consuming, I'll ask you to wait until the end of the class. But in any case, please ask. All right. So I don't see any raised hand, so maybe we can advance. All right. Okay, so with this, we have covered the usual homology case. Okay, so now let's look at the reduced homology case. Okay, now, I haven't still motivated why we are working with this reduced homology. So I agree with you. So please bear with me for the time being. When it is the right time, I will tell you why this reduced homology makes sense, and it will be like a one-line explanation. But that one-line explanation will, require me to define several things now. Okay, so let's just be patient. Okay, so let's look at the reduced homology case. So in the reduced homology case, the difference is that unlike in the usual homology case, the C minus 1, we now define it to be Z2, right? So the C minus 1 is again some vector space, but we define it to be Z2, right? So with this modified definition of C minus 1, let's see how this DABA minus 1 and this DABA 0 have to be defined. Right, so let's look at the case of DABA minus 1. So in this case, your C minus 1 is Z2, so it consists of two elements, 0 and 1, right? Whereas the C minus 2 is made up of this, it's a trivial vector space, so it is only made up of one element, right? So let's just understand what this, this C minus 1 is, and let's say what this C minus 2 is, right? So C0 only consists of 0, whereas this C minus 1 consists of two elements, 0 and 1. Right, so now we have to define this map DABA minus 1, which goes from C minus 1 to minus 2. Again, you can see that I have left with no choice, right? Because the codomain has only one element. So the only way I can define this map is I have to map 0 to 0 and 1 to 0 as well, right? So that's what I have done over here. And one can check that this definition is indeed a vector space homomorphism, right? So you can verify that. So this is how this DABA minus 1 is defined. Now we are only left with defining DABA 0. Okay, so this is the key thing that is different in the or in some sense is the main reason why this idea of reduced homology works and so on and so forth. Okay, so let's try to understand what this definition is. Okay, so let's first try to understand what is C0. Okay, so C0 is the set of all your zero chain. So it has 0, V1, V2, blah blah blah, VF0. Then you have V1 plus V2. Then you have V1 plus V3, blah blah blah. Okay, and finally you have V0 plus V1 plus blah 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 all the way up till VF0. So you have all these different zero chains. On the other hand, in C minus 1, you have 0 and 1, right? So this is now a tricky scenario, because now you have to decide, okay, which elements get mapped to 0 and which elements get mapped to 1. Is this okay? So the way this DABA 0 operator is defined is in the following way. So what you do is, let's say this is a generic zero chain that is given to you, right? So this is summation AI sigma I, where sigma I are your vertices. So I will say these are your zero dimensional faces, right? So let's say you have been given such a generic zero chain. So the output of this generic zero chain is written over here, right? So I hope you agree that this summation AI sigma I, okay, all these AIs are Z2 coefficients, right? So I hope you agree that all these AIs are Z2 coefficients. So what you do is you take these AIs and you add them up, right? So you add them up. So I hope you agree that since each AI is an element in Z2, you can add these numbers, and whatever will be the result, that will be an element in Z2. Is this okay? So for some AIs, this number will be 0, and for some it will be 1. And that's how you decide if you want to map this to this, this to this, and so on. So let's maybe do an example. So let's say I look at DABA 0 of 0, right? So DABA 0 of 0, you can sort of think of this as summation 0 sigma I, right, over all I. So this is should be, I mean, so the DABA 0 of this should be mapped to summation zeros, and all sum of zeros is 0. So this is 0. So one has verified that indeed 0 gets mapped to 0. Now let's see what happens if I map DABA of DABA 0, okay, of let's say one vertex. Let's say that vertex is V1, right? So you have to interpret this V1 as 1 V1 plus 0 V2 plus blah 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 all the way up till 0 VF0, right? And our definition of this DABA 0 operator is that you take the coefficients and add them up, right? So you add it up in this fashion. I hope you agree that the answer to this will be 1. Similarly, the output of DABA 0 of V2 will be 1, and so on. On the other hand, if you take DABA 0 of let's say V1, V2, V3, right? So this will be 1 plus 1 plus 1, which is again 1. So in this sense, you can see that all your V1, these single vertices, they like the zero chains which are whose support only is one vertex. Okay, so all those things will get mapped to 1. However, these zero chains which has a support of 2, meaning the coefficient is 1 for exactly 2 elements, those will get mapped to 0. I hope you agree, right? So in this way, if your support has I mean the support is over evenly many elements, those will get mapped to 0, and if the support is over oddly many elements, right, or an odd number of elements, those will get mapped to 1, right? So again, why is this definition useful and not? Okay, this I'm not explaining now. However, at this point you should know that this is how the definition is. Okay, later on I'll motivate why this definition makes sense. Okay, again, you have to be clear that the mathematicians, especially people like Enrico Betti, who was one of the pioneers of these these homology groups and things like that. Okay, so they didn't come up with these definitions right at the first moment, right? So they did lot of trial and error. Okay, they sort of tried to interpret what they are trying to do, what is happening. Okay, here is a definition, there are some issues with it, let me modify the definition. So there's a lot of trial and error happens, and eventually you come up with such definitions, right? And later on I will explain why this definition makes sense. At this point you only need to know how does this definition operate. Okay, so with this what we have managed to do is that we have this C minus 2 blah blah blah, C minus 2, C minus 1, C0, C1, C2, blah blah blah, right? So between each of these vector spaces there will be this DABA operator, which we also refer to as the boundary operator. We have managed to now define these boundary operators for any P. So I have finished defining DABA P for all P in the set of integers. Okay, in some cases I verified that DABA P indeed is a linear map, right? For other cases I did not, and I sort of left it as homework. Those who wish to verify should indeed spend some time in verifying them. Okay, so this is where we are right now. Is this okay? And one of the reasons for working with DABA P was that it sort of took these interesting patterns to 0, right? So that is where we are right now. That is, we have some intuition of why this DABA P is useful, right? And on the other hand, we have the formal definition of DABA P. Whether you are working with usual homology or reduced homology, we have this definition of DABA P for every P. Okay, so that's where we are right now. If you have any questions, please ask. This is a good time to ask. All right. Okay, so I don't see any raised hands. It's okay because we just did some basic definitions. Okay, but that's where we are right now. And then from here on, we can sort of try interpreting how is this DABA P useful, how is this useful to compute the homology, and so on and so forth. Okay, so but nevertheless, let's first begin by sort of recalling why we define DABA P in this sense. Right. So in particular, let's look at the case where this P lies between 1 and dimension of delta. Okay, so that's where the action happens. So let's focus on the definition of DABA P when P lies between this. Right. So we somehow claim that indeed DABA P takes these P chains of interest to 0. Okay, so let's look at another example. Let's say we have this simplicial complex. Okay, so this simplicial complex is made up of 4 vertices v0, v1, v2 and v3. Okay, and it has 4 faces. Okay, so I had drawn it in a certain way, but it hasn't come in that fashion. Okay, so let me maybe highlight what I'm trying to do. So there are these 4 triangular faces. So this is the first triangular face. This is the second triangular face, and then maybe I'll add another color. Okay, so this is the third triangular face. Okay, and then there is this fourth triangular face, which is basically the one that is there, which is made up of these 3 vertices v1, v2, v3. So you can see that there are 4 triangular faces, 1, 2, 3 and 4. So all these 4 triangular faces are present in this simplicial complex. Okay, so let's so the way to interpret this simplicial complex is that you have these so imagine a tetrahedron. Okay, so tetrahedron is you can imagine it maybe in this fashion. Okay, so maybe this is easier to imagine. So this is v0, this is v1, this is v2, v3. So I've sort of turned around this this figure that I've drawn over here, right? So all these faces are present. Okay, so all these faces are present. So you can see that this tetrahedron has 4 faces. So all the faces are present, but the interior of this tetrahedron is hollow. Okay, so that is very, very important. So this interior of this simplicial complex, let's say delta, is hollow. Okay, by hollow I mean that in this simplicial complex, in the definition, you have v0, v1, v2, v3. You have v0 you have v0 v1 sorry, v0 v1, v0 v2, blah blah blah, all the way up till let's say v2, v3, and then you have v0, v1, v2 and all the way up till v1, v2, v3. Okay, so you can see that you have 4 vertices. Okay, you have 6 edges and you have these 4 triangular faces, but you don't have any other higher dimensional face. Okay, so in particular the face v0, v1, v2, v3. Okay, this is not present. Okay, so maybe I'll put a cross here. So this does not belong over here. Okay, so this does not belong to this. So in that sense, I'm saying that the this interior is hollow. Okay, so clearly, because the interior is hollow, there is like a 3-dimensional hole here. Okay, so because the interior is hollow, there is a 3-dimensional enclosed region here. Right now, let's see if this Daba operator that we had defined earlier helps us identify this this hole here. So in order to identify it, what we am going to do is I'm going to give as input the boundary faces of this enclosed region. So observe that I give these 4 triangular faces. I take their sum. So I hope you agree that this is a 2 chain, right? So I take this sum. So this is a 2 chain and I give it as input to Daba 2, right? So now let's see what happens if I apply Daba 2. So as I mentioned, because this Daba 2 is actually a linear operator. Okay, so this should be Daba 2. Sorry, there is a typo. Okay, so because it's a linear operator, it will sort of split over the individual entries here, right? So I can so I can now I mean this expression over here equals this expression here, which is Daba 2 of this, Daba 2 of this, Daba 2 of this plus Daba 2 of this. Now we know how to compute Daba 2 of this. Okay, I just simply drop one of these vertices, right? So here I have first dropped the third vertex, here I have dropped the second vertex, here I have dropped the first vertex, right? So in this way I have computed the Daba 2 on v0, v1, v3. I first drop the third vertex, I get this. I drop the second vertex, I get this. I drop the first vertex, I get this, right? And in this way this corresponds to, okay, so this corresponds to this and this corresponds to this, right? So I'll sort of allow you to stare at the screen for a few seconds to indeed verify that at each of these instances I have dropped one vertex at a time. Is this okay? So maybe I'll pause here for a second or two for everyone to glance what is happening. Okay, and then what I observe is that you can see that here there is V0 V1, right, and similarly here there is V0 V1. So you can see that if I add these two things, this will cancel off. Now let's look at V0 V2. So here is V0 V2, and you can see that here is V0 V2. Now let's look at this V1 V2. So let's say this is V1 V2, right, and here you have V1 V2, and finally sorry, not finally, so here there is V0 V3, here there is V0 V3, and then here is V1 V3. Okay, so here is V1 V3, and here is V1 V3, and finally here is V2 V3, and here is V2 V3. So you can see that all these things occur in pairs, and since we are working with Z2, okay, all of them will cancel off and you will end up with 0. Right, so here is what you end up with, 0. So in this sense, again, you can see that this DABA2 operator is useful because, okay, if you look at these these boundary faces that enclose this three-dimensional enclosed region, if you give that as input to DABA2, indeed the output is 0. Right, so one of you were asking why are we working with this Z2 vector space. I hope you are able to appreciate the need or the use of working with this Z2 vector space, right, because we can easily cancel these things off, right, and that sort of helps, and in that sense I hope you are able to appreciate why we can work with Z2, why we need to work with Z2 vector space, sorry, Z2 field, sorry about that, I shouldn't say Z2 vector space, but why it makes sense to use the field to be the Z2 field. Okay, we could have as well chosen some other field as well, but the calculations then would have been slightly more complicated. Here they are very straightforward. Whenever these things appear at twice or evenly many times, okay, we can just simply cancel them off, right? Okay, so what I'm trying or trying to help you appreciate is that, look, this DABA-P operator that we have defined is very interesting. It's interesting because it takes these interesting P chains, in particular those that in some sense enclose these P plus one dimensional hole. Okay, so those are indeed taken to 0. Furthermore, okay, this is also equally important. If you have a collection of faces that does not enclose a hole, then that is not taken to 0. Okay, so let's look at an example. So let's say you have this as the simplicial complex. Here you have 3 vertices and 3 edges, right, and this is your simplicial complex. Now let's look at this chain, right? So this chain, so what is this chain? It is V1 V2 plus V2 V3. Is this okay? So I'm only looking at these 2 edges. Is this okay? I'm only looking at these 2 edges. So clearly these 2 edges do not themselves enclose a hole. Indeed, if I had these 3 edges, then it would have enclosed a hole. But at this point, I'm only looking at these 2 edges, right? And clearly, at least at a level of intuition, one can check that these 2 edges themselves do not enclose any 2-dimensional hollow region. So let's see if DABA1 takes it to 0 or not, right? So if you apply DABA1 on this one chain, what would you end up with? Well, the output of this will be V1 plus V2, and the output of this will be V2 plus V3. Okay, so here I would like to stress that when I write V2, I in fact mean this set which consists of the vertex V2, but I'm being lazy here. But even though I'm being lazy, I hope there is no ambiguity. Okay, this has to be a one chain, right? So if it has to be a one chain, then that means you have to interpret this as a set. All right, so you can see that here there is V2, here there is V2. We will cancel off these two things and we'll be left with V1 plus V3, right? So V1 plus V3 is not equal to 0 because recall 0, the 0 chain is 0 V1 plus 0 V2 plus 0 V3. On the other hand, you can see that you have 1 V1 and 1 V3 here. This is indeed not equal to this. So you can see that, if you had given these 3 edges as input to input to this DABA1 operator, you would have got 0. Whereas if you just gave these 2 edges, the combination of these 2 edges as input to DABA1, it doesn't take it to 0, right? So in this sense, you can see that the DABA-P operator is very special. It takes these special elements to 0. Okay, more formally, if you look at the kernel of DABA-P, right? So let's try to understand what this formal word means, right? So you have this operator DABA-P, and recall DABA-P goes from CP to Cp minus 1, right? So if you look at the kernel of DABA P, what does that mean? You look at the chains in Cp which get mapped to 0, okay, which get mapped to the additive identity of Cp minus 1. So this is what is the kernel of a linear map. Okay, so you know, whenever I say kernel, this is how it is defined. So you must have, you know, if you have taken a course on linear algebra, let's say T is a map from V to V prime, and if I asked you to define what is kernel of T, you would have said all little v in capital V such that TV is 0. Okay, so I'm sort of defining this kernel in the same sense over here. Now I'm claiming that this kernel of this DABA P operator is very interesting for us because it contains useful information about the number of P plus 1 dimensional holes. Is this okay? So this is useful because you saw that some of these P chains you know, which enclose this P plus 1 dimensional hole, those P chains are taken to 0, whereas those P chains which do not enclose a hole, okay, so of course we did not you know verify if this happens for every possible P chain or not, but this is at a level of intuition that look, this kernel of DABA P is, you know, serving our purpose in the sense that it is taking these interesting P chains to 0, whereas these P chains which are not interesting to us, not interesting meaning it is not enclosing a hole, those are not taken to 0, right? So in that sense this kernel is very useful for us, right? Furthermore, okay, this was one of the exercises in your assignment 1, right? That if you have a group, then it's and if you have like a group homomorphism, then the kernel of that homomorphism is a subgroup, right? So since we have Cp as a vector space and DABA P is a vector space homomorphism, the kernel of this vector space homomorphism would indeed be a subspace of Cp. Right, so that is something you need to keep in mind. We will be sort of exploiting the fact that this kernel of DABA P is in fact a vector space by itself, right? And since this consists of interesting elements, what we will say is that ZP, okay, this is the notation that we will use to define this kernel of DABA P, right? So this from now on, kernel of DABA P will be referred to as ZP. So this is a subspace of Cp, and the elements of this we will refer to as P cycles. Is this okay? So I think we are at the end of today's class. Okay, so we have done, you know, the definition of DABA P. We have tried to understand why it is useful. Okay, in the next class we will see what are the issues with this DABA P operator, and we will try to fix those issues. And once we are able to fix those issues, we will be able to reach a place from where on we'll be able to see, oh, now I'm able to indeed count these holes of different dimensions. Okay, so in the next class we should be done with that. So with this, let me stop over here. If you have any questions, please ask. In the meanwhile, let me stop recording.